Hello everyone. Today we're using Professor Alexander Giesing's lecture notes again. And the topic we'll discuss today is mainly about the discrete distribution and some other features and some very important case study of discrete probabilities like hypergeometric distribution and binomial distribution. So first we'll want to see an example because remember in the first lecture we defined what's a Laplace experiment. The Laplace experiment is uh, you remember every outcome is equally likely, but not every case has that property. So we would like to generate two experiments with outcomes that are not equally likely. So the first definition we introduce here is a discrete probability space. Consider a probability space with a sample space, its power set, and its probability measure is called discrete if there exists a finite or countably infinite subset D belongs to the sample space such that the probability that D happens is equal to 1. The associated probability measure is called the discrete. So here D you can treat D the same as the sample space, the omega, because the probability of D is equal to 1 and the probability of the sample space is also equal to 1. So they are just so it's just different notation about sample space. D and omega is the same thing. But just one important notice here is SD or the sample space must be finite or countably infinite, which means we can use natural numbers, rational numbers, or integers to represent, but we cannot use real numbers, the whole real axis to represent discrete probability space because the real number is uncountably infinite. So this doesn't satisfy that. And usually if we make the sample space with a real axis, the whole axis, we'll call it as a continuous probability space, not discrete probability space. Okay, so let's view a very simple example is throwing a fear die. And we have the sample space from 1 to 6, and and here the power set can be very large. It has 2 to the power of the cardinality of omega, which is 2 to the power of 6, which is 36. So just use this notation to simplify the all cases of the subset. Okay. And here we can use the probability measure and find out what that is. So we find that for each outcome or simple events, the probability is 1 over 6. That is reasonable because it's a fair die. So all of those events sum out to be 1, and each of them will be 1 over 6. And so that is the probability measure or probability distribution. It seems like all of the distribution will sum up to be 1, as here, like the probability of D is equal to 1. So D here is just 1, 2, 3, 4, 5, 6. And to give a more like precise definition, we'll say this as our final definition. That is, a discrete probability measure satisfies with the probability of any event A is equal to the sum up of all the probability of the simple events or the outcome. All of the simple event belongs to the event A. So here, we can also think in another way, like a discrete probability measure P is fully characterized by its values on simple events. So remember, every event is a set, and each set can be separated into of like disjoint, pairwisely disjoint subset of only one element. And if we sum up those probabilities together, the outcome is A. So that is what this definition is a sum of all the simple events of the simple events probability in A. We sum them up, and that's the probability of A, the event A. And there's some very vague and not very important characteristic of that. First is if the outcome in the omega is countably many, it has some number. But if it's not countably many, the probability of all the events, all the simple events, are 0. I would say this is easy to understand uh, because imagining there's uncountably many events and their sum is 1. So each of them must have no values. If any of them has value and you add them together, it will go to infinite. So that's what the first property says. And for the second one, it's very obvious. It's because probability must be positive or at least non-negative. So it is always greater or equal to 0. And the third one is that the sum of all the events sum up to 1. And that is also in the definition of a probability distribution. So that's our definition of discrete probability distribution. It's mostly about the same as probability distribution. I mean, any type of probability distribution, but the only one difference is its sample space must be discrete or has a finite or uncountably infinite subset D, such that PD is equal to 1. All right, so here's some proof about the property here, but I don't think that's really important for us to understand those. So if you are interested, you can see those lecture notes by yourself. And yeah, that's it. But why not we just see one example to see it all together? So first, there's a proof like let A equal to omega. So here is A is equal to omega, which means the A is any event and is equal to the sample space. Okay, and the A is equal to A intersect with omega. That is in the set theorem, not influenced that much. And we can divide the omega into a union of D and the complement of D, and use the distribution rule. We can go to this step. And one important thing here is because the A and DC, the intersection with those two, are pairwisely disjoint event. So their intersection is empty. And we got this because their intersection is empty. We can sum them up to be PA. And just because PA intersect with D is already D, and it cannot be larger than that. So PA is equal to PA intersect with D, and that's because PD is equal to 1. All right. So here we get one very useful outcome, that is PA intersect with DC is equal to 0. That is because and this is 1 minus, which means so here is PA minus this one, but this one is equal to PA, so this one is 0. That's like an addition and subtraction from equation. Okay, so what's going on next? Because D is countable, so A intersect with D is a subset of D. That's definitely great because A is not a whole set, but D, the property of D sum up to 1, but A probably is not. But in this question, it also sum up to 1 because A is equal to the omega. So from this statement, we can conclude that A intersect with D is equal to the union of all the outcomes or simple events in A intersect with D, and that's from the definition bar here. And yeah, and by definition 1.16, which is I don't remember which definition is that. But let's see what happened here is the probability of A is equal to the probability of A intersect with D, which is equal to the sum of all the events events like belongs in the A intersect with D, intersection with D, and that's very similar to this one. This equation very similar to this equation, and the power A, this equation is get from this formula here. So, and this formula is getting from this formula. This intersection, this union becomes sum because all of those simple events inside A intersection with D is all pairwisely destroying. So lastly, because for all the simple events not belong to D, the probability of them are 0. So we got this lastly is the intersection. The sum of all the simple events inside A intersection with D is equal to the sum of all of the events in A. The probability of every simple event. So this proof is for this one. So why the probability of any outcome that is uncountably many is 0. So that's a proof. And for the proof 2 and 3, you can think about more, but those are pretty simple compared to the first one. The first one is the most abstract one, and the second and third proof will be easier for you to understand. So I will not talk too much here. And let's see one example, that is ERM models. Remember, we talked about ERM models for 2 lectures before, and we are only talking about ERM models with one color of ball. Like you want to draw a certain color of the ball out, like, or even just with one simple color, like red, the whole red, whole white, whole black, whole yellow, whole green, whole blue, but it's just one color. The difference is just about their number. If you draw a number like number first ball, number 2 ball, number 3 ball. So in previous cases, we only considered balls with numbers, but now we also consider balls with colors. Consider with balls which are labeled 1 to N. And balls 1 to R belong to red, and R plus 1 to N belongs to white. So which means there's N balls total in the R, and there's R red balls and N minus R white balls, which sum up to be N definitely. And we draw N times ball at random from the arm, and its number or color is noted. So here we ask ourselves one question, that is, what's the probability that R red balls among the N drawn balls? So so here's the difference. We don't consider its number. The number is not considered right now. We consider its color, and there's 2 types of color, red and white. And want to see if we their relative number are already known, like it's just a ratio of like R divided by N minus R. But the question we want to ask is how many red balls can be drawn from a random drawing process. So and this only have 2 color ball, which is in this question, but in later concept we'll generalize 2 colors into more colors, like 3 colors, 4 colors, into infinite colors. And first we'll talk about one famous distribution, that is hypergeometric distribution. So this is a case very famous in, like, you want to select something from a factory. When the factory produce a group of, like, for example, cups, and a portion of the cup is it's like perfectly produced, but some cups are with flaws, and you want to select a sample of the cups they produce to predict like how many of the cups are, like what's the ratio of the cups that are damaged or imperfect shape. And this is an application of hypergeometric distribution. So first we'll see what it means. We draw at once n balls from the Earth. The event ER, that exactly R balls are red, can be drawn. So ER is exactly R balls can be drawn, which are red in the n balls. So here, obviously, the event is a subset of 1 to n. But remember, we draw n times, so the cardinality of A is n. But only R of them are red. So A intersect with 1 to R is R, and the remaining is n minus R, which is white. And here we say like A intersect with R plus 1 to n, which is not red set, is the cardinality is equal to n minus R, which then sum up to be the small n. And here's the lemma. So the probability mass function, or the probability like distribution function of a hypergeometric distribution is PR equal to R choose R, n minus R choose n minus R divided by n choose n for any of the R inside the set n to 0. And the probability of the event ER happens, which means the probability that exactly R balls are red can be drawn from the n drawing process is equal to that probability mass function. I want to write a proof about why this is correct. This formula looks very crazy with 3 combinatorics formula inside, but the logic is just here. We start the proof because we want to know that in our selecting process, R balls are red. There's like the capital letter R, the R balls. I want to select R from it. So it's just like R choose R. That's very easy to understand. But the remaining balls are not like to be any type. It can only be white. So from the remaining n minus R white balls, we want to choose n minus R white ball. So this is also n minus R choose n minus R. And because they're formed out to be the same event in the same level, we times them up. So use the principle of multiplication, we get the cardinality of the sample of the event ER is equal to R choose R times n minus R choose n minus R, which is here. Very obvious. And however, because we know from the want to see what's the sample space cardinality of the hypergeometric distribution. Well, first consider what's the sample space of that. The sample space is omega belongs to 1, is a subset of 1 to n. This is very easy because we just need one requirement, that is to choose n element from the capital N element. So this is the sample space, and its cardinality, because here we say it's drawn the balls out. Do we say it's okay? We don't say it's repeated or not. So there'll be 2 cases exactly. The first case is draw without replacement, and second is draw with replacement. But here I prefer to say it is draw without replacement, because we draw the balls out at the same time, so they are not replacing it back. So that's my deduction from the questions asking. So the cardinality from the last lecture, know if n balls are drawn, their order is irrelevant. And also they are not replacing back, which means it is without replacement. So the cardinality is just capital N choose N. So here, this question can be solved. And because this is a probability measure, so we use the event's cardinality divided by the sample space cardinality. So PER is equal to R choose R times M minus R choose M minus R divided by N choose N. So that's all about it. And also for the next part, this is already solved. Like here, we already know the probability mass function is in that shape for any R in the range of 0 to N, and if it's an integer, but we have not proved that it is a discrete probability distribution. So there's one more thing we want to prove. We want to prove that if we sum all of the PER together, the answer is 1. So if we can prove that, definitely we know it is a distribution instead of like any type of probability measure. So we know that E0, E1, E2 to the En is a partition of a sample space omega 3. How we can think about that? So you may think about it for the first several seconds. Okay, so hopefully you already know why that case is. It's very simple because N balls are red, which means there cannot be one ball is red. So En and E1 are partition, and E1 and E2 are also like destroying event, because if you have one ball red, it cannot have any other number of ball are red. So those are all like pairwisely destroying events. So that forms a partition. Because one of the requirement, the prerequisite for partition is all of the events inside that set are pairwisely destroying, and also the sum up to be 1. Right? The sum up to 1. Is that correct? I really doubt that, because we don't say it's probability, so it might not sum to be 1. It just said a cardinality, so it sum up to be any type. We don't know how big the N is, but it can sum up to based on that formula, it can sum up to any number. It's not linked to N directly. We also will consider the capital N, which indicates how many elements totally from the population. And because we know there is a partition, so the sample space so the sample space is equal to the union of R from 0 to N. We sum them up, and because all of them are disjoint 1, and R is not equal to S. The S here means the N. So I think this is just N. It's not X, because we don't talk about any S before. So if R is not equal to N, then this one sum up to be 1, and PR is equal to the PER. So the probability measure on this omega and fancy A becomes 1 to the N, and this is the sample. So the sample space we choose from, and its power set is 2 to the power of the omega, and omega is this step. All right, so we finished the proof about this formula's credibility. But in most cases, you are not really required to remember how it is proved. If you can use it in reality, it's good. But if you want to push yourself more intense in understanding the real logic behind, you would like to write another proof by yourself, assisting with those slides, the lecture slides. And now we'll see one example. One totally finished example is the fish in the pond. Suppose there are n fish in the pond, n1 of which are red, and 2 of which are yellow. You catch k fish in a net without returning them to the pond. What is the probability that you caught exactly k1 red fish? So there's too many variables here. I want to define one by one. So first, which variables shows the fish number? The n is the total fish in the pond. N1 is the red fish. N2 is the yellow fish. And K is the fish that you catch. And K1 is the red fish that you catch. So the sample space as illustrated above, this is a hypergeometric. This is a hypergeometric distribution. So the sample space is equal to all of the which means all the event has the cardinality k, all the set with cardinality k, that is a subset of 1 to the capital N. And from this formula above, which is, let me see. Yeah, we might talk about that before, but it's this formula. So it's N, capital N choose N. So in this question, the cardinality of the omega is N choose K, capital N choose K. And so the next step we are discussing about the probability that K1 red fish and K minus K1 yellow fish. This condition also stands. And we just add brackets to A. So the cardinality of A is equal to N1 choose K1 times N minus N1 choose K minus K1. And this is exactly the same from our proving process here. Here we have the proving process. And once we know the event's cardinality and also the sample space cardinality, we know them both. We just divide them together to find out the final probability of the event A happens. Or we say it's the K1 red fish is caught and K minus K1 red fish is caught, given by picking totally K fish in a pound with N1 red fish and N2 yellow fish. So this question is solved. So let's go moving on to the last important theorem about our class is the binomial distribution. So in the binomial distribution, we draw n times from n with replacement. The event ER that exactly all balls are red can be written as ER equals to A1 to AN. This is the set, but only those AI belongs to I are in the set 1 to the R, which means red balls, and the remaining one are yellow balls or non-red balls. We'll define a non-red ball here as white ball, so there will be a consistent example to the previous example. So the sample space here is A1, A2, A3 to AN. And all of those A1, A2 to the AN belongs to set 1, 2, 3, 4 to the N, to the capital N. This is a sample space, and it's very easy to understand if you follow the lecture here. And the event ER, as we said before, it definitely contains the same amount as in the sample space. The difference is just only all terms of those A's are in the red one, not in the white one. And definitely we get a very quick formula here. The probability of ER is equal to the probability mass function PR is equal to N choose R times R divided by N times to the power of R times 1 minus R divided by N to the power of N minus R. And R is in the range of 0 to N. This is reasonable because R cannot beyond N to to have more radials than both or have negative radials. And I want to like to prove why this works. So first we'll say the each ER as they are all disjoint union of adjacent set. So consider for each I means I here represents the R. I is a range, it's a notation of R here. And if we say if we want to describe the event of EI happening, just AI belongs to the capital I are in the range of 1 to R, but the AI outside of the capital I set, they will become like R plus 1 to R plus 2 to the capital N. And that's all. And if we do it clearly, we want to talk about the ER. So how ER works is for all of the set I. For all the set I. The set I has one thing in common, that is their cardinality or set size is equal to R. So we union them out, union all the set I with cardinality R out, and we found the union to have the cardinality of R to the power of R times n minus R to the power of n minus R. If I is a subset of 1 to n, and the cardinality of I is equal to R. So how we can interpret this one? This is because the R is number of radials. If you have imagining you have R radials as I equal to R. So obviously, very obviously, you will have R numbers of radials which are chosen from the capital R options. So that's why we say R, the small r times of the capital R exists. So that's capital R to the power of small r. And with the same logic, we'll say the number of white balls we choose, which are not red balls, are n minus r to the power of small n minus r. And we time them together by the principle of multiplication, and we get the cardinality of EI is equal to this one. And so let's consider let's consider more. So this case only considers one particular case, like the how to say, like the order is fixed. Like the first R must be R, the second is R to the. It's like a list. It's with a fixed order, like 1, 2, 3, 4 are red balls, 5, 6, 7 are white balls, and that's a 7-ball example. However, that is not best in our example. The first to be white 1, or first to be white 3, or first to be red 1, or first to be red 10 can be different from each other. So we just add times the permutation into this formula above, into this formula, and we get n choose r times r to the power of r times n minus r to the power of n minus r, and we add permutation together to count the order into consideration. And this is the sample size this is the set size we get for the this is set size we get for the event, for this event, exactly R balls event. And also, because we know the cardinality of the sample space omega is n to the power of n, because there's in each step there's capital N choices, and we chose it n times. So we get capital N to the power of small n. And since all outcomes in omega are equally likely, so we have the probability of ER is equal to ER cardinality divided by omega cardinality, which is n choose R times R divided by n to the power of R times 1 minus R divided by n to the power of n minus R. So this can be confused at first. You think of why we just divided by n to the power of n. So why we got that one? So the previous formula is here, but we can separate the n to the power of n into two parts. That is n to the power of R and n to the power of n minus R. So if we times the n to the power of R here, we get R divided by n to the power of R. And if we get the n to the power, the second half is n to the power of R minus n, n minus R, and it's n minus R with n minus R divided by n, which is 1 minus R divided by n to the power of n minus R. And that will solve. And because we also proved from the same logic before, like all of those events are partitions, like partitions of like omega. So so now we can conclude that this is truly a probability distribution, not arbitrary probability measure on any set. And we can now say the sample size is the sample space is 0 to n, with its power set to be R to the power of the omega. That was solved. So maybe it's very abstract and you will not feel comfortable to understand. But another example might help you in understanding. So the last example we show about like rolling a dice, and now we give another example of toss a coin, and it's a toss a fair coin n times. What is probability that coin shows heads exactly k times? First, we'll consider the sample space. The sample space is because you choose k times, it must have the size k. Because you toss n times, it must have a size of n. So the tuple here, or the tuple here, is a1, a2, a3, a4 to an. And that's how we got that. And we can say each AI from here can only be H or T, which represent head or tail, because this is a fair coin problem. And so this is exactly the same as the ERN model 1. So we can use 2 to the power of n to represent that, because the size of the sample it can choose from is 2 and has n component and element in that set. So this is from 2 lecture before, and this is from the lecture today, because we get k times h, which means we select n choose k permutations of the events 1 to the power of k times 1 to the power of n minus k, because there's only for h there's only one choice, for tail there's only one choice, so it's 1 to the power of k times 1 to the power of n minus k, and 1 to the power of k, the power of k is the head probability possible ways, and 1 to the power of n minus k is the tails probable ways. For calculating the final probability, we just use the probability of A is equal to the cardinality of A divided by cardinality of D, which is equal to n choose k times the n choose k times the probability of 1 to the power of k times 1 to the power of n minus k divided by the sample space cardinality, which is 2 to the power of n. And Remember, this is a fair coin. This is a fair coin, so the probability of getting head and getting tail are exactly the same. So we can use n choose k times one times 1 to the power of k times 1 to the power of n minus k divided by the 2 to the power of n. And we can exactly like what we did before to separate term 2 to the power of n into two parts. So we get 2 to the power of k times 2 to the power of n minus k, and we separate them into this formula. So we get the PA is equal to n choose k times 1/2 to the power of k times 1/2 to the power of n minus k, and we are solved in this one. So there's one more case. It's called the multinomial distribution. The multinomial distribution is the more color setting of the color ball example. So here we define an N model with many color balls as consider an N with n balls, which are labeled 1 to n, with the first n1 balls of color 1, the second n2 balls of color 2, the third n3 ball of color 3, and continue this pattern, the last nr balls of color R. We draw n times a ball at random from the and its number and color is noted. So imagine there's R colors of ball, and we choose n of them out. And originally in the set, they are n1 first color ball, n2 second color ball, and R color of balls. And I want to find probability that we draw exactly n1 balls of color 1, n2 balls of color 2, and nr times of balls of the color R. And we can introduce a new concept to that. It's called the multinomial coefficient. So this definition says the number of possible ways in which a set A with cardinality equal to k can be partitioned into n subsets a1, a2, a3 to the an with cardinality k1, k2, k3 to the kn, such that k1 plus k2 plus everything continue to kn, or plus until kn is k, and this can be represented by this formula. And you should remember this formula for this course. And it has another way to represent is this one. It's the multinomial coefficient, which is the extended version of the binomial coefficient. So remember, in the binomial coefficient, the k here is k, but here is like k. Oh, here is n. Yeah, here is like n factorial, and k factorial times n minus k factorial. But here k is the n, and we can view the previous k times n minus k as k1, n1 and n2, and now it becomes k1, k2, k3, more k until kn. However, if for any of k, if it's not greater than equal to 0, or it doesn't sum up to a, it is 0, because this doesn't exist, and we define it as 0 if these two conditions are not met. So back to this question, how can we know if there only contains n1 both of color 1, n2 both of color 2, n3 both of color 3? So we use this formula. We use the multinomial coefficient placed above in the replacement of the binomial coefficient, and we time all of those small terms one by one. K1 divided by n1 divided by n to the power of k1, and times change k into 2, 3, 4 until r. So this is the formula for solving that question. And remember, all of the n1 until NR belongs to natural number with union with 0, and N1 plus N2 plus should equal to N, and the probability of A, N1, N2, N3 to the NR is equal to the mass function if it works right, if it works ideally. So that is the expected outcome we'll see. So this is the lecture for today. And if you have more questions, you can ask. But I will reply in a comment if you leave a comment beneath the video. And yeah, so today we talk a lot about like very abstract concepts. Like I remember what is the difference between distributions, probability distributions, and probability measures. We discussed that in the last lecture. But if you have more questions, you can first practice or leave as a comment for me, or just you can email me for getting more information. And this is like a turning point of our lectures. And starting from next lecture, we're drawn to an even higher level to discuss about independence, probability independence, and conditional probability. And they will be much harder. And they'll not be error models and not be just Laplace experiments. Those all of the things we covered before, like discrete probability space, are just a small portion in conditional probability. And the conditional probability or independence are more formula-based and ask you to prove whether it's conditional, or you can build a tree of decision tree to determine, okay, whether it's how to say whether it is independent or not, or it has some variable has an influence on other variables throughout cases. And that's our next lecture's content, I believe. Hopefully you will enjoy this lecture. And good luck to you all.